Chapter 6, Section 2, Differential Equations, Growth and Decay. In the previous section, we verified that an equation was a solution of a differential equation. In this section, we will find the solutions of differential equations and then use them to solve growth and decay models in applied problems. Yes, real-life word problems. So to solve a differential equation, they give you a differential equation like this, and the steps are, first of all, rewrite y prime as dy dx. For this, we like Leibniz's notation for derivative a lot better because it will help us separate our variables and then integrate both sides of the equation and then rewrite it using strategies to get rid of fractions and solving for y if it's possible, but if not possible to solve for y easily, then just solve for the constant. So let's follow this example. If y prime equals 2x over y, we're going to rewrite y prime as dy dx and think of dy separate from dx. So step 2 is to separate the variables. That's an easy step to forget, but an easy step to complete. Multiply both sides by dx here. And then your dx's will cancel, and then multiply both sides by y. So you'll have y times dy on the left side and 2x times dx on the right side because those y's will cancel. And now we're just going to integrate both sides. So to integrate y, you add 1 to the exponent, divide by the new exponent. That's our y squared over 2. And that gives us y squared over 2 plus a constant. We'll call this constant number 1. On the right side, we add 1 to the exponent, which becomes 2, and then divide by the new exponent. So then we're going to be multiplying by 2 and dividing by 2, so that those 2's will cancel out and we'll just have x squared plus another constant. We'll call this constant number 2. Now if I subtract a constant from both sides, don't I end up with just another new constant? So we'll call that a constant. You can subtract x squared from both sides, so then I'd have y squared over 2 minus x squared equals a constant. But I still have this fraction. So what I want to do is multiply both sides by 2. And if I do that, I'll have 2y squared over 2, so those will cancel, minus 2x squared equals 2 times a constant. Well, 2 times a constant is still a constant. So you can write it like this, y squared minus 2x squared. Or if I had put the constant on the other side, or factor out a -1, you can get the signs to change. So if I factor a -1 out of this, I'd have a negative y squared plus a 2x squared, and then a -1 on that side, divide both sides by -1, you end up with 2x squared minus y squared equals, what's a negative c? Still a constant. So the order that you write these, whichever side you put them on, won't matter. This answer is just as good as this answer. So either one will be equivalent. So watch for that on your homework when you're checking your answers in the back. If you end up with this and they end up with this, you should be able to recognize that they are exactly the same answer. All right? In many applications, which means real-life problems, the rate of change of a variable y is proportional to the value of x. If y is a function of time, the proportion can be written as, so here's the rate of change of y with respect to t, is, and then proportional to y means times y. Proportional means times a constant, and k is the constant that mathematicians have chosen for this. So the rate of change of y, using this, the rate of change of a variable y is and proportional to the value of y. That key phrase there is going to alert you to the fact that we're using an exponential growth and decay model. So if you start with this and you separate the variables, because this is a differential equation, you separate the variables, integrate, solve for y if possible, you end up with y equals c, some big constant, times e to the kt. We call that sect. C is the initial value of whatever y represents. It could be initial population, initial amount of money, initial amount of a radioactive element, whatever we're measuring using a growth or decay model. K is the constant of proportionality, which we usually have to find. That's not given to us. T obviously is time. And y is the amount of the thing that we have left over after however much time has passed. All right? So, like I said, applications such as radioactive decay, population growth, continuously compounding interest, declining sales, lots and lots more applications of exponential growth and decay. So let's prove this. I told you that this would end up to be sect. Well, let's talk about actually how. So multiply both sides by dt. So I have dy equals k times y times dt. Divide both sides by y. So I have dy over y equals k dt. Now that k could really go on either side because it's not a variable, it's a constant. But let's keep it on the right side. So now that we've separated our variables, we have everything with a y on the left side and everything with a t on the right side. Now we can integrate. What's the integral of dy over y? And that looks like natural log of y to me, plus a constant. But I know I'm just going to add that constant onto the other side later, so I'm just going to put it on the other side at the end. All right? And the integral of k with respect to t is that constant k times t to the first, plus some constant. Now, I wanted to get to the, I've integrated it. Now I want to solve for y, if possible. Well, how do you get y out of a natural log? If you remember, we exponentiate both sides. So that kt plus c is the exponent of e, and e has an exponent of natural log of y on the left side. Well, the natural log and the e undo each other, so we're just left with absolute value of y equals. Do you remember what happens when you have a variable or a constant raised to a power that's added? Usually we don't think about it this way, but think about if you had like x squared times x to the third, and I wanted to multiply them together. Remember, our shortcut is to add the two exponents together, so then we would end up with x to the fifth. Well, what we have here is like this. We've got a base, which is our e, and then we've got an exponent, which is an addition problem. We're going to go back and rewrite it like this. So we're going to break up that e to the kt, and then times, because that's what the rule is, times e to the c. What we've always done in the past is we've started with something like this and wanted to add them together to get to something more simplified. But what we're doing is breaking it up so we can rewrite it. So we're taking this addition problem, or this problem with an addition in the exponent, and going back to what it was before we applied the rules of exponents, or the laws of exponents. So now we have e to the kt times e to the constant of c. Well, e is a constant, and if you raise it to a constant, that's just one big old constant. So this whole thing is just a big constant. So we have a constant. Remember, let's think about the sign of this constant. If e is raised to any power, it'll always be positive. And this e raised to any power will always be positive. Even if t is a negative value, it'll still be a positive value for e to be raised to that power. So a positive times a positive will always be a positive. So are these absolute value signs necessary? Nope, they're not anymore. So y equals a big constant, we'll call it c, times e to the kt. And there's our sect. So now that we know that if we ever have any sentence in the beginning of a problem that says that the rate of change of y, that's this side, is proportional to y, then we don't have to work through all this stuff to get to an equation that relates t and y. We can just assume that this, which is the sentence I just said, morphs into this. So we can just use this equation. All right? So here's an example. The rate of change of y is proportional to y. Then when t equals 0, y equals 4. And when t equals 5, y equals 1/2. So they're giving us 2 points that are on the graph of whatever this rate of change of y is proportional to y is. Well, we know that the rate of change of y is proportional to y translates to this. Rate of change of y is proportional to y. But when we solve that differential equation, we know we end up with this. So now we can use that solved differential equation plug in the values they give us, and find the value for C and the value for K, because those two variables we don't know. We're going to use t equals 0 and y equals 4. So when t equals 0 and y equals 4, we get 4 equals c e to the k times 0. What's k times 0? That's 0. What's e to the 0? That's 1. What's c times 1? C. So c equals 4. And remember what c stands for? It's our initial amount. Does that make sense that when time equals 0, if our amount is 4, that 4 was our initial amount? It should. So if you're given t equals 0, you can just go ahead and plug a 4 right in there, because you know that putting 0 in here for time is going to end up just giving you c equals 4. So now our equation looks like this. Y equals 4 e to the kt. We still have to find k. So let's use this other information. When t is 5, y is 1/2. So let's plug 1/2 in for y, and then t is 5. So now we have 1/2 equals 4 e to the 5 times k. We want to solve for k, so we've got to get the k out of the exponent. The first thing we're going to do is divide both sides by 4. So on the right side we have e to the 5k. Now 5k. I'm going to be running a 5k in May with my family. It's the rave. Has anyone ever heard of that? It's like a color run, but not, you don't get painted, it's just like you wear glow-in-the-dark colors. It's a night run. Anyway, back to calculus. 1/2 divided by 4 is the same as 1/2 times the reciprocal of 4, which is 1/4. So that will be 1/8. Now how do we get the k out of the exponent? Again, we take the natural log of both sides. So we have the natural log of 1/8 equals the natural log of e to the 5k. Natural log of 1/8, you could rewrite that. Natural log of 1 minus natural log of 8. And on the right side, the natural log of e to a power is just that power. What's the natural log of 1? That's 0. We don't know the natural log of 8 offhand, so we're going to keep that in that form. And then that equals 5k. Solving for k, we're going to divide both sides by 5. So k equals negative natural log of 8 divided by 5. So that is a decimal. We don't want to round it, because, or change it into a decimal and have to round it, because k is a very important proportionality constant here. If it's even rounded too much, it'll throw off our whole equation. So we're going to write our final equation as y equals 4 times e to the negative natural log of 8 over 5 times t. And now we can use that equation. We could graph it. We can use it to find any values of y when we know t. So if whatever this thing is, if it's money, if it's carbon atom, if it's some kind of chemical that decays, whatever it is, or this one looks like a growth one because notice decay, it started at 4 and then it's a 1/2 at 5 seconds or years or billions of years later. So what's the value of y when t equals 3? We can just plug a 3 in here. And so we can calculate that with our calculator. Y equals 4 times e to the negative natural log of 8 over 5 times 3. Now when you're using a graphing calculator and you want to get that decimal value, remember to store it as something like letter K. Ooh, that would be convenient. Store it in letter K, and then every time you want to use it, you can just type in 4e to the, and then the letter K times 3. And then you could use that for different numbers here. And then not have to keep retyping in negative natural log 8 over 5, etc. So that value, when we plug in 3, I didn't calculate that out. I'll let you guys do that. All right. Let's talk about a carbon atom. Carbon-14. Does anyone know what carbon-14 is used for? I believe it's used for carbon dating. So when they find something like a bone, archaeologists find a bone that's been buried for years, they can do some carbon dating with it and find out exactly how old it is. Not sure, but pretty sure that's what they use it for. So the half-life of carbon-14 is 5,730 years. If you understand how half-life works, after 5,730 years, however much we had to start with, there will only be half of it left. And then again, 5,730 years later, there will be half of that left. That's what half-life is. So anything that decays or has a half-life, after that many years, there's only half of it left, so it's decaying. So if we have some carbon-14 that has a half-life of 5,730 years, if 4 grams remain after 10,000 years, let's find the initial quantity, so how much did we start with, and the amount remaining after 1,000 years. All right, so how are we going to do that? Well, we know that anything that decays follows this pattern. Y equals C e to the k t. So if there's a half of it left after whatever we started with, so if you end with a half, you started with 1, and how much time did it take? 5,730 years. So this concept here, you can plug in any number for C if you want. Let's pretend we started with 10, so you could write a 10 there. Oops. And then what would you have over here? After 5,730 years, you better have 5. So you can fill in any number here that you want for the initial amount. All we're doing is trying to figure out what k is. So we fill in any initial amount here and put half of it over here, and that will help us find k. I chose 1 because it's much easier to solve for k when I have a 1 here than if I had a 10. It would just be one extra step here dividing by 10, and notice if I did take that step to divide by 10, I'd end up with 1/2 equals e to the k times 5,730, which is what I would have started with here. So it just eliminates one step if you start with 1/2 equals 1 times e to the k times 5,730. So now we're going to take the natural log of both sides, because we're trying to get that k out of the exponent. So on the left side we'll have natural log of 1 minus natural log of 2 equals, and the right side the natural log and the e cancel each other out. We just have 5,730 times k. So this is 0 minus natural log of 2. And I'm going to divide the right side by 5,730 and also on the left side. So I have negative natural log of 2 over 5,730 equals k. So now my equation, y equals c times e to the negative natural log of 2 over 5,730 times t. Okay, I did all that work just to find k. I still haven't answered even the first question, which is find the initial quantity. Well, now that I have an equation, or a partial equation, I have k, I can find c using 4 grams and 10,000 years. Y is the amount remaining after t time has passed. So 4 grams is the amount remaining of whatever we started with after 10,000 years have passed. So fill in the t and the y. Calculate this whole exponent. Raise it to the e power so that you get a value. And then divide both sides by that number. So the exact value is c equals 4 over e to the negative natural log of 2 over 5,730 times 10,000 years, which is about 0.4097 grams. So that's approximately what we started with. The computer's lagging a little bit here. Alright, so that's question A. Question B, how much is the amount remaining after 1,000 years? Well, now that I've answered question A, my equation, remember I rounded it to 3 decimal, usually you want to leave your decimal answer rounded to 3 decimal places, but I'm going to be using this number again here. So it's better if I round it to at least 4. It's even better if I just store that value, store this in my calculator, maybe store it as C, and then I can reuse it here. So I would type in y equals C, using whatever stored value I have here, times e to the k, and maybe I stored that in k, and then times 1,000 years. So the less typing in, the better. So after you calculate a value like this, just store it in k and store this in c, and then you wouldn't have to retype it all. So we'll have a number here times e to the negative natural log of 2 over 5,730 times 1,000. So all of this multiplied together is about 11.88. Well, that's messy. .882 grams. Remember to either round or truncate at 3 decimal places. So that is my answer for B. That's my answer for A. Initial amount here and amount remaining after 1,000 years. Here's your homework, and we'll finish up with part 2 tomorrow.